welcome to BKW Physics. I'm Mr. McConley, and today we're going to talk about energy. Now, energy comes in many, many forms, and in physics class, high school physics class, we're going to deal with mainly with the five I have written on the board here. Now, let's start from the left-hand side. PE, meaning potential energy. Now, potential energy is energy that's based on your height above the Earth's surface. So it's a height-based energy. And the equation goes, potential energy is m times g times h. That's a reference table equation. So m is mass, g is gravity, h is height. There's really nothing that tricky about that. You've seen it before in probably middle school science. Ke is kinetic energy. And kinetic energy is based on motion. So when something has motion, it's going to have kinetic energy. But the ones that get tricky for some people are thinking about sound as being kinetic energy, because sound, you don't see it moving, but I hope further in the year when we talk about sound, you'll understand that sound, the way it moves and vibrates, lands it under kinetic. Anyway, the equation for kinetic energy is 1/2 mv squared. Mass, velocity. Velocity is a squared term, so it makes more difference than the mass. So if you increase your mass of your car, like you get a heavier car, that will give you more kinetic energy as you drive down the road. But if you increase the speed that your car is driving at, that is a squared term, so it makes more of a difference. All right? So just real quick to focus in on this for a second, frame your mind a little bit. If I threw a baseball, and I was good at throwing a baseball, and I could throw it like 60 miles an hour, you'd probably be a little scared of just letting the ball hit you, because a 60-mile-an-hour baseball will hurt. It could knock your teeth out. If you're not paying attention, it causes a little bit of pain. Well, what about a 60-mile-an-hour car hitting you?
Kill you pretty much.
Yeah, I mean, unless you're just real lucky or get deflected somehow, it probably will kill you. So you realize in that case, you're holding the velocity the same, because I said 60 for each one, you're just changing the mass. So that's one way to look at kinetic energy. But instead, if you took the baseball and you threw it one time at 30 miles per hour, and then you take the same baseball and you throw it at 60 miles per hour, you've doubled the speed, but what have you done to the actual number here? Like, what's a 30 squared? 900. What's a 60 squared? 3,600. 3,600. So you've gone from 900 to 3,600. This number has gotten way, way, way bigger when you doubled the speed. That's what I need you to understand about that one. There's elastic energy. For right now, I'm just going to go check. We're going to talk more about that another day. Elastic energy is anything that's stretchy. We'll get back to it. Then you're going to jump into internal energy. Now, internal energy is something you've already seen when you were in chemistry, and usually it took the form of Q equals mc delta T. For that, mass, specific heat, and change of temperature. And then there were like Q equals mhf or hv, heat of fusion, heat of vaporization. Those are internal energy. And what they're based on is they're based on temperature and phase, the phase that you're in. Now, that doesn't seem very physicsy, does it? Well, because that's not usually how we talk about it. What we usually talk about is, so start this part of it, what we usually talk about is how does friction play into this? Well, the way friction plays in is friction causes heat, okay? Friction causes heat, and therefore you're adding to the total energy of the system when you have friction. If you have more friction, you produce more heat, you got more internal energy. So that's where the internal energy, the way we usually talk about it. This is all good stuff, but we don't usually use, we don't use the equations in physics, really. And the last one that comes up often on the Regents is they refer to mechanical energy. And a lot of people go, what? What is that? Well, mechanical energy is simply defined as your potential energy plus your kinetic energy. So if you're talking about mechanical energy, you're going to take and find these two things, add them together, boom. Now, a really important thing to understand here about this, and we'll come back to this concept also, is that for a falling object, this is constant. Mechanical energy is a constant. Because as the potential gets less, as you're dropping down and the potential gets smaller, you're picking up speed, so this one's getting more, but when you add them together, you keep getting the same number. So this is a constant when something's falling, which is usually what they're referring to when you're doing a Regents question. So I've kind of given you an overview of energy, and hopefully it's not too terribly confusing, but really the point of today is, how does energy tie into work? Okay, well, so far you've done that work is force times distance. Fine, easy enough. But when you look on the reference table, you will notice that they have an equation written that work, this is the way it's written on the reference table, W equals F times D, and it's equal to change in ET. This is reference table verbatim. So what they're saying to you here is that work is force times distance. Yeah, got it. But work can also be equal to the change of total energy. Where are they going with this? Well, to investigate that a little bit further, I'm going to take you through a quick little rearranging. Work is force times distance, right? Force is mass times acceleration. True? So mad right now. But I'm going to break down distance a little bit further. Remember the equation Vf squared equals Vi squared plus 2AD? What if we were to rearrange that and solve it for D? Let's do it real quick. Vf squared minus Vi squared, we divide it then by 2A, and that's D. So if we throw that back in here, we got M times A, and then we got Vf squared minus Vi squared over 2A. Alright, well, what if we think of a falling object again? If we think of a falling object, what's your initial velocity when you drop the thing?
0.
0, so let's kind of drop that for now. And then, what do I want to do here? I guess I want to do, oh, there's an A on the top and an A on the bottom. Let's get rid of those. It's just like a simple cancellation, right? So now I'm getting where I want to get. If I take, there's a 2 on the bottom still, if I take that and pull it out as a 1/2, you know how you can do that in math. If I leave the mass where it is, and I'll leave the velocity where it is, except I just won't be so specific about it, what does this equation all of a sudden become? It becomes kinetic energy. So I guess what I'm trying to show you here by this simple demonstration is that you take work, and by tweaking it around a little bit, you can show that work is the same thing as kinetic energy. So what this equation ends up showing you is that work is the same as kinetic energy, work is the same as potential energy, work is the same as elastic energy, and we can go through the different examples and you can show that work and energy are the same thing. Before we end this, because we're going to have to come back to that topic on another video, but before we end this, back to my baseball example. So if you throw a baseball, you can give the baseball some kinetic energy. Easy to understand, right? But let's approach it from work now. If I go to throw a baseball, do I apply a force to the baseball as I'm trying to get it going?
Yeah.
Force, 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 over a distance. So I applied a force over a distance. So I could calculate the work. I could say, oh, I did this much force times this much distance, boom, come up with a number. Well, guess what? As soon as I stop doing the work and the thing releases from my fingertips, do you know how much energy it has, kinetic-wise? the same amount as the amount of work I did to it. So whatever work I do to something will, in turn, be how much kinetic energy that thing has. So for today, physics.